Well, thank you everybody for coming along to the latest talk in our Optics for the Cloud series of public talks, and we're very pleased to have Rupert Oulton with us today from Imperial College, and he graduated from Imperial with a PhD on optoelectronic microcavity devices, and went on to research plasmonics and metamaterials at Berkeley. He's back now at Imperial and is particularly interested in the optics of metals, and that's what he's going to talk to us about today. So just a reminder that there'll be chance for Q&A afterwards, of course, and then please, particularly if you're one of our external visitors, we will have a few bits to nibble and maybe a glass of something to drink, and please stay with us and enjoy a little post-talk discussion. Thank you.
Good afternoon, everyone, and thank you for asking me to come along and talk about a little bit about the work that I do at Imperial. I think it might come across as very researchy for the kind of application-driven science that you do here. But I hope that there's something that you can pick out of this that might be useful, or it might jog something, an idea for future collaborations and the like. So I have a lot of diverse interests. Research today is difficult to get funding, and you kind of have to spread your wings and apply for money in lots of different areas, and this is essentially how the chips have fallen. So I came from, when I was in the US, I was looking into nanolasers, tiny lasers that potentially could be integrated on chips for communications, but also how small could you make a laser? And it turns out we can make lasers that are actually smaller than the wavelength of light, which was a big surprise to us. Since then, I've moved on to look at some more weirder types of laser, condensates of light. Light being bosons, they can undergo Bose-Einstein condensation. This is kind of very new topical research. We just got a new grant on recently. I'm going to talk in this presentation today more about these other two topics here, nanophotonics and metamaterials, and light-matter interactions between 2D materials, graphene and similar materials, with optical antennas. And the theme of my talk, acknowledgements first. So I work, I'm at Imperial College in the physics department, in the experimental solid-state physics group, actually. But in our group, we have a lot of research on optoelectronics, whether that be with organic or inorganic semiconductor materials. So anything to do with light matter interactions is covered by the experimental solid-state physics group at Imperial. We also have work going on with the photonics section at Imperial too, and the quantum optics section as well. We interact with the materials department as well at Imperial, and we have long-standing collaboration with King's College London with Anatoly Zayats there. Recently, Stefan Meyer, who is also at Imperial, just moved to Ludwig Maximilian University, and we have strong ties there as well. So these two faces here, these are the main people who've done the work that I'm going to talk about today, my students. Michael's in Australia now, looking at solar cells. I think he found this work a bit too blue sky. He wants to do something a bit more useful, at least for the planet. And Victoria is currently in Oxford, researching 2D materials. So this is the outline of my talk. What is metal optics? You usually think about metals as reflecting light. What else can they do? And that's what I'm essentially going to show you today. And the examples are, I'm going to show you how you can create an antenna, just like a radio antenna, but something that responds to light at optical frequencies, and how this can then be turned into something called a metasurface. Okay? All will be made clear when I get there. I'm then going to talk about a different aspect of these metal structures, and that is the capability to squeeze light, in fact, any form of electromagnetic radiation, into a space that's considerably smaller than the wavelength of that excitation vacuum. And how this leads to extreme light-matter interactions. I'll give you an example about a nonlinear process, mainly because it's extremely weak and we make it strong. But there are many other types of applications that you could think of. Anything to do with sensing would be the par for the course for this kind of study. or technology in the future. Finally, I'm going to talk about photodetectors because it's quite interesting that if we play around with the structure of metals, we can actually make physical things happen with the absorption of light and photodetectors. So I'm going to show you how the structuring of a material can lead to better absorption and photodetection rather than having to choose the material and the band gap of the material to create that absorption. Okay, so what is the central theme of metal optics? Well, it turns out the diffraction limit, if you think about the microscope objective, try to focus light down to as small a point as possible. You can focus it down to about lambda over twice the refractive index of whatever is your imaging medium. Likewise, if you try to look at objects in the focal plane of a microscope, this is about the scale to which you can resolve those objects. But it turns out that this is a consequence only of the fact that transparent media have low refractive indices. Okay? So since Arber came up with this diffraction limit, it seems we've been tied to the wavelength of light in optics, but we've had no reason to be tied to that. So this is how it works. In fact, the only thing that does not change for an electromagnetic excitation is its frequency. So if I shine light through a medium where I've changed the medium from refractive index 1 to refractive index 2 and back to 1, what happens is that the light slows down and its wavelength gets shorter. And they do this to compensate for the fact that your frequency does not change. Okay, so the other thing is that we have these waves, they've got a certain wavelength, and if we want to focus light using a traditional lens, what we will do is we will shine lots and lots of rays at different angles, and they interfere in the focal plane of our lens. And essentially, this is the phase front of a wave traveling at a certain angle, because it's been focused by this lens. And then the transverse wave number here, it can vary as a function of angle, and all these interfere, and if you add them all up, you'll get something that looks like this. And this represents the spread function of our lens. That's the smallest point to which, or smallest shape of field we can generate with our lens. And you'll find that this is about lambda over lambda over n times sine alpha, the largest angle you used. So this is ingrained in history now. This is Ernst Arber's statue, which shows his diffraction limit formula as I've expressed it with an extra factor of 2, but who's counting? So, of course, Arber was around in Jena. This is in Jena. He was around at the same time as Schott and Zeiss was the engineer, Schott was the material scientist, and Arber was the physicist. And they all got together and made the best microscopes and lenses in the world. Right, but the point is, this is only because we think of transparent materials with a refractive index that's quite small. In fact, in the visible and near infrared, the largest refractive index of any transparent material you'll find is about 4, which is pretty bad. Go to microwave regime, RF frequencies, you can get higher refractive indices, but at optics, it's about 4. Right, so why is this a ludicrous thing? Why are we not restricted by the wavelength? Well, you're doing sub-wavelength electromagnetism every single day. This is a plug, obviously. And between about the centimeter distance between these pins, we get very efficiently 50 hertz electrical signals, and they power our devices, etc., etc. But when you think about it, the wavelength of a 50 hertz electromagnetic wave, well, it's gigantic. So the British Isles is lambda by 6 in this case. So we are definitely capable of working below the wavelength. So what is it? Oh, this is another example. This is our microchip. 2 gigahertz is typical speed for a microchip these days. That is a wavelength of 15 centimeters, and yet the little channels, the feature size, in fact, for the transistor gates is about 32 nanometers. These wires themselves that join transistors are a bit larger, and this is now pretty much smaller since the 5 years I've had this slide. I think we're sub 10 nanometer now in terms of transistor channel sizes. And in a nutshell, you can do the same thing with optics, but you have to use metals. So this is a structure which we designed when I was at Berkeley. It's got a metal substrate. It's got some semiconductor components on the top. The main point is that we launch light through the back here, and it coupled into this funnel and got slotted down all the way to here. And then we brought in this tip, and this tip We scan it over the surface of our structure, and it scatters light out where it's strongest. And we were able to show that really the light is trapped between this yellow material and the silver. So this is a semiconductor, and this is some metal. And this is about 50 by 150 nanometers, and it's for a He-Ni laser, so this is 633 nanometers of wavelength. And the side of this picture is pretty close to the wavelength. So it just shows that with optics, we can do the same thing if we use metals. So the free electrons in metals, they interact really strongly with light. They're free electrons. You shine light on them, they move. In fact, that's why light gets reflected from a metal so easily. But more importantly, metals generate optical excitations that are limited in principle only by our ability to fabricate those structures. What the hell do I mean by this? In order to talk about this, I have to go into a little bit of detail. And the detail concerns these excitations. They're called surface plasmons. What's a surface plasmon? Well, they are, quite frankly, just natural solutions to the wave equation when you look at the interface between a metal and a dielectric. And they are true surface waves, in fact, because they can propagate in the plane, but their electromagnetic energy dissipates away or decays away from the surface. So there's no energy propagation away from the surface, it's only in the plane. Okay? So a general picture of this, what we can do is we can represent these waves. Generally, when you want to look at a new type of excitation, you look at its dispersion. That's the plot of energy or frequency versus its momentum. And these are excitations that are trapped to the metal surface, so they're moving slower than any excitation in either the air or the metal. So they're trapped below what we call the light line here. And if you think about metal at really long wavelengths, it becomes completely opaque. You get reflection from light at long wavelengths, very conductive at those frequencies. And so very little light penetrates into the metal, and it looks like a sort of glancing angle wave that propagates along the surface. In fact, the Earth itself has a sort of conductance which allows surface waves to propagate over it. And this is how radio waves propagate. But at high frequencies, the metal becomes more transparent. Okay? Eventually, when you reach the plasma frequency, light will be able to propagate through metal. But just before that, enough energy sits in the metal that these surface waves can exist, but also they take on a lot of energy or a lot of momentum from the electrons that are involved in the oscillations. And this causes this turnaround, this increase in momentum as you increase the energy. And eventually you get to a place where surface plasmons can no longer exist. And that's about the UV, about 350 nanometers. It changes for different metals, but that's the kind of region. So in order to understand where confinement comes from, we have to look at what's going on at this metal surface. So in this next slide, I've just zoomed in on this wave. This is essentially the plus minus the change in polarity of the wave as it's propagating in space at a fixed point in time. And if you look at what's going on in the metal here, if I zoom in on what's going on, within the metal, you can think of electromagnetic waves. They're trying to move electrons around, but as these electrons are moved, all the electrons around them, they move as well, and they try to screen any residual charge that may occur because you've moved an electron. So within the metal, it remains essentially charge neutral. And it's only at the surface where there are no electrons in the dielectric region, these cannot compensate for the electrons that are being moved. And so what you get is this very thin layer of surface charge. And this is the origin of these field lines that define the field distribution of your surface plasmon. So crucially, this turns out to be about 1 angstrom. So it really is very thin. It's thinner than the interatomic spacing, for instance. If you want to go there, you have to go into quantum mechanics and do some terrible things. I want to keep this as a classical optics lecture, so we won't go any further than that, although I'm happy to talk about it later if you have questions. So, can we make things that are this small, smaller than the wavelength? Well, these are chemically synthesized gold nanowires. I don't have a scale bar here, but the diameter of these is below a micron. And so, if you think about the cross-section, this is what a surface wave would look like traveling along a nanowire. And it looks pretty much like the surface plasmons that propagate on the plane. It has a charge distribution. This charge distribution changes polarity as the field propagates as a wave into the plane, into the screen here, as it's propagating. So the way to understand where confinement comes from is to realize that while the planar surface has an exponential decay, when you curve this surface around, you can have a different field distribution. Okay? If it's a really small curvature, it will look just like a plane wave. A plane surface plasmon, if the curvature is very, very large. But if the curvature is very, very small, you can imagine, for instance, that you're trying to resolve something that moves further and further away. This essentially looks just like a single positive charge, or negative charge, depending on the phase. So eventually it looks like just a point charge. So we know that plasmons have an exponential decay that's tied to the wavelength, but a point charge has a 1 over r decay. And what that means is that the field amplitude will decay by half in a distance that's equivalent to the radius of your wire. So what I mean to say here is that the size of your field amplitude is now not linked to wavelength, it's linked to the size of the structure that supports the wave. If we can make a smaller structure, we can make a smaller, more confined wave. So if you are mathematical, the mathematical description of the light for a nanowire is a Bessel function, modified Bessel function, this K function here. It doesn't matter really exactly what it is, it's given by this black line. And you can see that this black line, in different length scales of distance, you have a 1 over r squared decay and you have an exponential decay. What that means, if it's a tiny nanowire, it's like a 1 over r decay. If it's a big nanowire, it's exponential and linked to the wavelength. So I have a movie here that just shows you, or illustrates, this is from a course that I teach at Imperial, it illustrates the effect of this confinement. So here's the electric field distribution from the nanowire plotted from, so actually this point here is near the center of the wire. So this is 0 point is the interface between the metal and the dielectric. And this is the field decay of the light away from the surface. This dotted line represents what happens for essentially the infinite radius of curvature. And this is the starting radius of curvature, which is radius of 5 microns. Okay? So as we decrease the size of the nanowire, oh, where's my mouse? It's missing. Oh, there it is. It's a very simple plot, just to show you, as you shrink the radius of the nanowire, what happens is that the field becomes more and more confined. So I haven't changed the wavelength. All I've done is shrunk the diameter of the nanowire. Here we've got 1 over r decay for the small wire. Here we've got something linked to the wavelength. Okay? Interestingly enough, this is purely geometrical. Okay? So before I showed you that when surface plasmons are being confined or being operated near ultraviolet waves, the momentum shoots up because more electrons are involved in the process of storing the energy. Here, this is the momentum here. The momentum is only increased by less than 5%. So this is really to do with the geometrical electric field pattern that a point charge has, or a point line charge. What am I doing? Okay, right. So now imagine I've got this nanowire and I truncate the ends. Okay? So now I have something that looks a bit like an antenna. So this antenna, if we have lots of different frequencies, for instance here, you've got the wavelength plotted from 400 nanometers, that's blue light, all the way up to 2 microns, that's already into the mid-IR, against the rod length. Okay? And each of these lines represents a different diameter. Okay? As you change the diameter, you change the speed that waves propagate along, and so you change the condition when the phase is pi by 2 that allows you to have a dipole antenna. Just like a radio frequency antenna, but now it's for wavelengths approaching the visible and near IR. Okay, so as you shrink down this rod length, all of these conditions, this essentially the resonant wavelength of one of the antennas is linked to the length of the antenna. These linear relationships all basically converge on one single point. Okay? At this point here, at this wavelength, you cannot have a surface plasmon excitation for a smaller structure. In fact, if you make it smaller, you still have the excitation, it just doesn't change wavelength. So, this is, I'm sorry if you've already seen this, but in our field, I suppose it's a bit of a running joke, but this always used to be the thing people used to describe this condition for small antennas. This is the Lycurgus cup at the British Museum. It's quite interesting because depending on how you look at it and where the light source is, it looks different. Okay? So what you have essentially is white light shone from one end, and inside this, the glass of this cup are metal particles. These metal particles are very small. And what you'll notice from this plot here is that when you make these gold wires smaller and smaller and smaller, they all converge on the same wavelength. So providing all the particles are small enough, they will all have a resonant wavelength at about 500 nanometers, which is green light. So here we have all these particles, which are small enough so that they all scatter green light. So if you look straight through if you essentially have the light source behind the cup, this is what you see, a nice red cup. Light shining through it, looks quite interesting, pleasant to look at. What's happened here, essentially all the green light has been removed. It's been scattered all the way around in different directions. So if you now look at the cup from the side, you should see it looks different. It looks green because the light that's been scattered is the green. Okay, so I've talked to you a little bit about how metals can generate optical excitations that are linked to their structure, their size. And there's many interesting consequences because of that. The final thing is about what happens. So my final theme is that light-matter interactions can be greatly improved in strength with this kind of optics. So electronic and optical wave functions can be matched in scale to create extremely fast optical processes. What do I mean by that? Okay. So we have to go back to, remarkably, 1947 and 1946, where two different people had some very interesting ideas about how antennas radiate and how the radiation of an antenna can be improved. So the first one is the Wheeler-Chu limit. So this is the paper from 1947. So this chap was an engineer, and what he was doing was looking at these little dipole antennas. But he said that these antennas, if they were smaller than the wavelength, a lot smaller, there was a really simple formula for telling you how quickly the radiation could come off your antenna, essentially the radiation rate from the antenna. And this is the formula. So this is the frequency at which you're operating. This is the rate at which light is being lost. This is some geometric factor, and this is nothing more than the ratio of the volume of your antenna and the wavelength cubed. So the wavelength, the volume wavelength, and the wavelength of the volume of your antenna. What do they mean by the volume of the antenna? Well, quite simply, if you have an antenna, for instance, this little U-shaped antenna is commonly used in the literature. Its length scale is about 50 nanometers. If you draw a sphere that encompasses it maximally, so the edge of the antennas touch it, this is what the volume he was talking about. If you do the calculation, you find out that this antenna, being so big, about 50 nanometers in scale, it's not that big, is it? I'm going to show you some things that are smaller in a minute. This antenna has a radiative rate of 100 femtoseconds. So I've designed this actually for 1 micron wavelength, so this is just on the cusp of the near-infrared, 300 terahertz, and the optical period is about half a femtosecond, okay? So essentially what this means is that this antenna holds on to the radiation for about 200 cycles before it dissipates it to the surroundings. So the atom is an interesting situation. An atom is just an antenna. It's holding on to some radiation and it's going to radiate it. But it's so small that the radiation is very, very, very slow. In fact, at these frequencies, most atoms, you have to look for atomic levels that have dipole moments on the order of the Bohr radius, but if you plug the Bohr radius into this equation, you come out with millisecond timescales, and that's pretty comparable to what you get. Okay, so now an atom essentially has a dipole that oscillates for millions and millions of times before it can lose its energy. And I always put this example up because I'm a solid-state physicist. Semiconductor materials have things called excitons, And these are actually delocalized, so electrons and holes, they're whizzing around each other like a hydrogen atom in a crystal. The length scale of those is about a nanometer, and that corresponds to the time scale that excitons live for, about a nanosecond. So what this means is that most light emission processes, because you could think of them as antennas, they radiate very, very weakly, inherently slow. Okay, so now I'm going to put you with the most exciting paragraph of my field of nanophotonics. It's probably the most highly cited single paragraph in science. I don't know if that's true or not, but I reckon it is, by how much it's been cited in our field alone. So this is Edward Purcell, got Nobel Prize for nuclear magnetic resonance. He realized that the rate of emission or the rate of transition of any process can be enhanced if you couple it to a resonant circuit. And he was using the example of nuclear magnetic states inside he was looking at nuclear magnetic states, and he says here that because okay, I'm not going to go into it. Essentially, the nuclear magnetic transition would take somewhere on the order of 10 to the 21 seconds, i.e. the age of the universe, even longer, to undergo a transition, so it can never be in thermal equilibrium. If you couple it to a resonant circuit, he showed that this could be done in minutes. So this is quite remarkable because it's a 20 order of magnitude change in the transition rate of something. And you can apply the same principles to optics. And indeed, this is what people do. This is the formula that Purcell came up with. He said you can change the natural rate of emission. All you have to do is put it into a resonant cavity that has a size. So this is lambda cubed over the volume now, not of the atom or the antenna, but of the optical resonator, or radio resonator, whatever it is. And then it's modified again by this thing called the Q factor. The Q factor is once you've got radiation held inside a cavity or an object or an antenna, it resonates around for a little bit before the energy is lost. And this Q represents how many times light's bouncing around inside this resonator before it dissipates. So people have used photonic crystals to see enhancement factors approaching 100, but in metal optics you can do better because you can shrink down the size of your optical modes dramatically. So in the photonic crystal case, you can get high Q factors, but you're always limited by the diffraction, or by the fact that refractive indices of transparent materials have low refractive indices, are very low. With this metal optics approach, you can do anything you want with this volume. Well, the Q factor doesn't work so much because metals dissipate energy, but this volume reduction gives you a remarkable enhancement. And this essentially, this is the state of the art after a decade, Purcell factors of 100. This is the state of the art after perhaps 5 years with plasmonics. It's a Purcell factor of 1,000. Okay, so what I want to illustrate here is if you take this idea of Wheeler and Purcell and put them together, because in effect Wheeler was talking about this parameter here, Purcell is talking about the modification of that parameter. What you find is that any interaction rate between light and matter is just linked to how big the antenna is with respect to how big the optical mode is that you're using to access it. So the ratio of the volumes of the material state and the optical state, and of course modified also by the Q factor, how long the light hangs around before it dissipates. Okay, so I'm going to skip that and I'm going to come on to this point here. So this is what I really view is going on in plasmonics and metamaterials, or metal optics today. You've got light at the diffraction limit up here. This is on micron length scales for a wavelength of about a micron. And you've got the characteristic length scales of electronic states. And in metamaterials, what you're trying to do is you're trying to make bigger antennas that can interact better with light beams. And for plasmonics, what you're trying to do is you're trying to shrink down the scale of light so it can interact better with very, very small things at the nanoscale. Okay, I'm going to skip this. And I'm going to skip this. These are just some examples. I want to get on to what I'm going to say here. So why metal optics? Well, It's about decoupling the scale of optical devices from the wavelength. You can strengthen light-matter interactions with the plasmonic approach, making fields small. You can define new materials that can mold the flow of light. That's the metamaterials approach, which we'll talk about in a minute. And the mantra really is function through structure. I'm going to show you a few examples now. One of the first questions that I was asking when I joined this field is that how well can we interact with a single antenna? So these are two objectives, confocal arrangement, and we've got a little disc antenna. So it's not a bar anymore, just a disc. And remarkably, this interaction can be very strong. And the reason it can be very strong is that if you think about this antenna, it's like a dipole when it's excited. And that means that it radiates like a dipole. Dipole radiation looks like this. So it's concentric waves coming out from a point source. You also have to make sure that you align your electric field along the direction of the dipole, so it has a little bit missing here, but that's okay. Right, if you now think about a focused wave, just shine a plane wave onto an objective lens, it gets focused down, what does that look like? It looks pretty much the same. Okay? Concentric waves, in this case, for the focused wave, the light's coming in and out, and for this case, the waves are always leaving from the point. So this represents our antenna. This represents the excitation wave, the plane wave. So actually, the overlap is really good. And this paper here, it showed that if you had a perfect dipole, which didn't lose any of its energy and it just purely radiated, if you focus light down on this, it would give you 86% reflection or something like that. So this guy is actually working on trying to get reflection, 86% reflection from a single atom inside a vacuum chamber, for instance. Quite a remarkable idea. So this shows you what happens if you illuminate with a focused beam a single metal disk. This extinction represents 1 minus the transmission of the light through the particle. So you can see that 60% of your light, you get a 60% drop in transmission for one of these particles. It also shows you that the smaller your particle, the more weak the interaction is. This comes back to what I was saying earlier. Actually, if you want a strong interaction between light at the diffraction limit, just conventional classical optical beams, you actually need antennas that are quite big. You can also see here that when you go from 60 nanometers to 110 here, the wavelength doesn't change very much. Again, this comes back to the point I was making. If the antenna is small, it's actually not particularly malleable in terms of its ability to engineer it. It's only the larger ones that show tunability and this very high extinction. Okay, so when we were doing these experiments, we were pretty shocked about how sensitive the particle is to the focus beam. I've been telling you that you need a larger particle to be able to get good interaction between light and the particle. But the problem is here, this is to show you that actually the particle is still very, very small and very sensitive to its position in the beam. So we did this experiment. In fact, when we started doing this, we couldn't understand our results at all for this very reason. And it turns out the reason we can't understand it is because of chromatic aberration. And it's so sensitive as this technique is that it allows us to measure the chromatic aberration of any optical imaging system. So chromatic aberration is when any lens, they try to introduce different glasses to compensate for chromatic aberration. But inevitably what happens is that red light and blue light come to a focus at different positions. If I now drive my particle, which incidentally is just 50 nanometers thick, through the focus here, what I will do is I will have a slightly different spectrum of extinction because the blue and the green light and the red light are all out of focus. So this would be the real extinction of the particle, and at different positions I would see a different extinction. So we did this experiment. So if you're really cheap and you don't want to spend too much on a lens, you buy something called an achromat. It's corrected for 2 colors. So this is the true extinction of our particle. These are real experimental results now. And this was the best position where 2 colors were in focus, but all the other colors are out of focus. And if you spend more than £6,000, you can buy something called an apochromat. That is corrected at 3 colors now. So this is the true extinction of our particle. We've got a different particle now with a much broader response. But you can see that the 3 colors are in focus together, but it's It's pretty annoying having to work with these things when the different colours are in focus at different times. If you want to spend a lot of money, you can buy something called a super achromat, apochromat, and it's in focus at 4 different colours. Anyway, Nikon were pretty surprised when we showed them these results because so these are the positions of the focus at different colours. So here you can see this slice here shows you that 2 colours were in focus for this particular position of focus. This shows you that 3 colours were in focus. They were surprised because the best they've got, it takes them many days to measure this using interferometry with lasers at all different colours, so they get points at different places. So they were pretty shocked when we said it took us 10 seconds to do these measurements in each case. So nanoparticles are pretty sensitive things. So this was a bit of a hero result, the next one. I just really was interested in whether we could do it or not. These antennas, they extinguish light, but they also change the phase of the light, because that's exactly how extinction works. You've got this scatterer, it's scattering light out of phase with the light that's exciting it, and that's how it cancels out. We wanted to measure this phase change. So what we did is we took light on this beam splitter here, and what this beam splitter did is we put 2 beams in, and 2 beams came out, and we tilted the beam splitter so that these beams came at different angles inside our objective. One beam gets focused to a different point, so the change in angle shifts the point at which it comes to a focus. And what we did is we had a beam that was exposed to a particle and a beam that was not. And so all we did was we measured the phase difference between these 2 light beams. When they come back through the next objective, essentially they come back and the beams are overlapped but have a very small angle. And when light is essentially within the coherence length, when it's a small angle, it will create interference fringes. And so indeed you get interference fringes. We put it through a prism and that resolves spectrum. And we got this really nice plot. So this is white light that's been split into wavelengths in one direction, but interfered with a reference beam in the other direction. So you can see that the spacing between these waves increases as the wavelength increases. And this was the residual phase. So these are flat to within 0.1 of a radian. So it was a pretty nice technique. Anyway, the point is that this is the extinction of the disk I showed you from before. This now shows you the phase of those disks. Okay? So why did I show you this? Well, the point was to show you that you're not just cutting light out, you're dynamically changing or coherently changing the way these antennas are interacting with the light. So you're shining a beam on, and then the antenna is then radiating that light with a different phase to the light that's coming in. And this is key for the area of metasurfaces. So what is a metasurface? Well, all you do now is you make an array of these antennas. So here, these are little gold antennas or representations of them. And what you can do is you can change subtly the properties of each antenna, and then it will scatter light at a phase that is dependent on its position in the plane. So now, for instance, if I were to grade the phase along here from linearly, what you would find if you shine a plane wave on, it would re-radiate, and this light would be refracted, okay? As if this were a different medium of different refractive index. This is mimicking the effect of an air-glass interface, but it's essentially no thicker than 50 nanometers of gold. Okay? So this is the principle behind the area of metasurfaces. So this is not a very good resolution here, but essentially what metasurfaces plan to do is to take bulk glass optics, which are heavy and thick and non-compactable in terms of the portable technology we love, and convert it into a very, very thin layer which can be integrated on something flat and flexible and whatever you want. So these are all the sort of things that people are doing in the literature. The field is so saturated that there's very little money available for this, so it's not something that I'm researching at the moment, but it's something that I'm quite interested in. The other great thing about this field is that we don't want small antennas. I just said that they don't radiate very well. So actually, we can get away with dielectric antennas. So these structures here are just little blocks of transparent material. Yeah? and they're actually very big compared to the wavelength, but they allow you to do flat optics. The benefit of that is that all metals have a little bit of absorption, and the dielectric metasurfaces are pushing 80-90% efficiency. So it's really possible to do optical components that are flat and transmissive pretty good. Okay, from optical antennas to metasurface. So large antennas interact strongly with optical beams. Optical antennas with focus beams are aberration sensors. They're, this very sensitive to position. But it tends to be that people make arrays of particles now, and these arrays, because each antenna can radiate with a certain phase, and that's controllable in space, you can make something called a metasurface to guide and mold the flow of light and do whatever you want. And since large antennas are required, dielectric structures with low loss are possible. Right. Okay. I think I'm doing okay for time. So something that really got me interested when I joined this field in 2006, God, it's been quite a while, was a recent paper at the time by a chap called Mark Stockman. Incidentally, Mark Stockman also proposed that you can make tiny lasers, so that was another motivation for me. So what Mark Stockman proposed is that you could taper metal structures in such a way to confine light to infinitesimally small points. His proposal was, take that nanowire example from the beginning. If you were to gradually shrink the nanowire diameter down and down and down as light's propagating along it, will it deliver all the energy to the tip, or will it scatter the energy, or whatever? Anyway, so what he did was a simple calculation, and he showed that, wow, all the energy can be transported to the tip without reflection or scattering, and you can have this phenomenon called nanofocusing, which he coined, incidentally. Nanofocusing is perhaps a strange word because nano is only relevant in the optical domain. If you were to do this with microwaves, you could do sub-wavelength focusing just by making these kind of structures as well. But the point here is to do it with optics. The only problem is that he was really, really optimistic about what we can make. He wanted a cone angle of 1 degree. He wanted the diameter to change from 50 nanometers down to 1 nanometer. Bear in mind that I think if we make a 50 nanometer structure, we're pretty happy with ourselves. And this is actually very challenging to achieve. What can you actually do with this technique? So it wasn't long after, in 2007, where I got a bit disappointed because people started reporting on this topic. This shows you a scanning electron microscope image of one of these cone structures that someone literally thought, I'll do exactly what the theorist said. What he did is these grooves here, they allow you to shine light on them and launch waves, these plasmonic waves along the nanowire, and they should be focused to the tip. And I thought this demonstration really clearly showed the whole point of nanofocusing. So what you see here is a schematic, and these position 1, 2, 3, and 4 show you where the illumination was put onto this tip. So firstly, we have illumination right at the back end here. And you can see that nothing much happens. It just illuminates the nanowires, you can see there. Right. Next thing is they illuminate the front of this grating. What you see is launching of plasmon waves, and we see this tip lighting up really brightly. So this presumably is the nanofocusing effect. We're able to couple light to this tip because we are launching to waves that are creating the right conditions to generate waves that go right to this tip using this nanofocusing phenomenon. But they went further. They then focused the light a bit closer to the tip. Well, in this region, you don't see much. And then they went straight ahead and said, well, I can just illuminate the tip. Presumably, I'll do better. But you don't. The point is, when you illuminate the tip, this is quite an expansive distribution of light compared to this. Remember that this point source here is diffraction limited. We can't actually see how small it is. But you can see here this is definitely a diffraction limited, not a diffraction limited point source. The energy is distributed over a very large space. So these guys have done fantastic scanning probe microscopies using this technique. It really is quite nice. So I was more interested in nanophotonics, and I think this is something perhaps that you're interested in here too, about how optical data communications can improve our data capacities and energy efficiencies. So this work is from the Leuthold group at the ETH in Zurich. This work is from a Japanese group, and I think it's Natomi group at NTT. which is the telecommunications company out there. So what they've got are simple standard silicon waveguides, and they taper them down and launch light into these metal groove structures. It works pretty well, and what they're doing here is they're putting a material inside this, and the light and material interact with each other, and they apply a bias, and when they change the bias, they can modulate the light that passes through this structure. So this is actually becoming commercial technology now. People have always thought and put to one side the idea of using metals because they're so lossy, but Leuthold is pushing forward to this. These things, they only have 3 dB insertion loss, and they can be extremely short. For instance, these kind of modulators are typically millimeters in length scale in current optical devices, but these can be just microns. This is their wow result. This shows the ability to couple 90% of their light from the silicon waveguide into a ring resonator now, this gap ring resonator, and then they use this as a modulator. Okay. So the reason I brought up these examples is because they are quite difficult to make. And what we've been doing is coming up with a really simple technique that's a test bed for all the things that you can possibly do. So this was our demonstration. Essentially, we got something very similar to what the Leuthold group and other groups have done. We've got this gap structure. This supports a very strongly confined mode in the gap. In fact, this shows you the field distribution that you would expect for light in this gap. Very high intensity here. Okay, how does this work? Well, maybe this is beyond scope, actually. I will skip it. Okay, the main point about this idea is that we don't actually have to do very much nanofabrication at all. We can buy off the shelf a silicon wafer. It's got this thin silicon layer sitting on silica. And then all we do is deposit a little bit of silica and pattern on top of it metal structures. And this metal structure in particular, this gap structure, is very interesting because if you have a wide gap, the light sits in the silicon and it propagates fairly low loss. If you now have a very narrow gap, the light gets pulled up into the gap and gets focused down. So what we've essentially got here is a very simple way of making a nanofocusing device. All we have to do is change one geometric parameter, and we can use lithography. It's very easy to do. And essentially, this is what we've done. These are all little waveguides with in-couplers and out-couplers, and you can see here the little waveguide gap structures. And very little fabrication required. So how do we prove that we've actually focused the light down? In fact, there are not many demonstrations that can show this because the light really is in such a small space. The only way to prove that it's actually doing anything, or you're actually getting focusing, is to look at some effect. So the Leuthold group makes a better modulator because the gap is small. But no one's really seen how that light is strengthened. So this is one of the first demonstrations to do this. And what we did is we put light emission centers inside this gap. So we're getting to remarkable distance scales here now. So this is the structure as you see it on the SEM. If you zoom in, you can see that there's about a 25 nanometer gap. And in here, these little white dots, these are semiconductor quantum dots. And they emit light in the range 600 to 700 nanometers, so on the edge of the visible towards the red end. And what we do is we illuminate this grating structure and we launch infrared light at 1.5 microns now. And we entice illumination, excitation and luminescence from the dots at the higher frequency, at 600 nanometers. So in order to do this, the quantum dot has to absorb 3 photons and then emit them. So what you can see here, this is the one that I think is the most important one to show you. This shows you a scan, or a line scan through this structure that shows the focusing. So this here, this bump, is the illumination from the spot. So that shows essentially 3 photon absorption and luminescence from the dots from our input spot. And this shows the 3 photon absorption and luminescence from the dots that are in the gap. And you can see that this enhancement intensity it's quite staggering. So this is direct evidence for a focusing effect. You can also see that this excitation dies away quite quickly. This is the the fact that light waves inside a very confined metal structure are subject to losses, and they decay away. In this case, though, it's 3 times shorter than the distance they propagate because it's a 3-photon absorption effect. It scales with the electric field to the power of 6 because of the 3-photon absorption. This shows you a slightly wider gap. You still get the focusing, but in this case, the excitation from the input beam is a bit more prominent. So generally we can test any structure before we make it using something called finite difference time domain. So we essentially look at electromagnetic problems. We divide space up into divisions in space and time, and we let light go into our structure, and we can monitor how light accumulates in various regions. And this is just to show you that there's a rigorous simulation that shows how it works. So this is the silicon structure here. So all of this is silicon. And this region here, light is pulled from the silicon as it propagates into the gap. And you get this really nice enhancement in the gap. These are cross-sections through the structure here now. You can see the light sits in the silicon waveguide modes, pulled into the gap as it propagates along. Okay? It's very difficult to measure exactly what the efficiencies are here. But if you shrink the gap down to about 20 nanometers, which is the smallest size in this simulation, we end up with an 80% coupling efficiency. And literally last week we found an error, and it's 94% coupling efficiency. And I pushed my student on it a lot because I thought 80% was a bit low. It's 94% coupling efficiency. These things can be really, really useful, I think. The other thing is that the intensity is enhanced by 400 times. Yeah? And this is not the intensity relative to the input beam. This is the intensity relative to the light that's sitting in the silicon that you've generated in the first place. So what's the point of all this? Well, we want to generate really, really high-intensity light, because if you can generate high-intensity light, you can get extreme interactions between light and matter. When does a light field become strong? Well, it will become strong when you can ionize electrons from the material and completely destroy it. All right? So that actually sets the limit, because other than that, there are people who are going to intensities where you can basically separate electron-positron pairs generated from vacuum. So, and that would be so high intensity, probably 30 orders of magnitude higher than anything I consider here. But we're considering material damage to be the limit. So if you look at the Coulomb field, the electric field that binds electrons in matter, you find out that this is somewhere in the region of 10 to the 16 watts per square centimeter in terms of intensity. People make lasers that go up to 10 to the 30 watts per square centimeter these days. But we don't necessarily want complete ionization. It turns out that DC breakdown in a tunnel junction would be about a volt per nanometer. That's corresponding to 10 to the 12 watts per square centimeter. And there's a phenomenon called high harmonic generation, where essentially nonlinear optics become very strong. That happens around 10 to the 12 watts per square centimeter as well. So if we take the laser system that sits in my lab, and we think about the intensity enhancement we can get with what I've just shown you, it turns out that we only need an average power of about 100 microwatts to make this, to create an intensity that would destroy our material. Or not quite destroy our material, but would get very, very interesting effects. What is 100 microwatts? Well, a laser pointer is about a milliwatt. Okay? Now, the light here is pulsed, so it's actually squeezed in time into higher intensity. But the average power, the average energy of the pulse over a long period of time is no more than the power you have in a laser pointer. So this means that you can do portable, really strong light-matter interaction physics. And that's what's really exciting for us. So this is going to probably into a bit too much detail, but we wanted to show that not only can we see the focusing effect here, we can get a strong effect. So there's a phenomenon called four-wave mixing, which is useful for telecommunications, incidentally. It allows light signals to talk to each other. Usually light just interferes with itself. It doesn't deflect itself or change its direction or anything. But when you have a very intense beam of light, the light will modify the medium in which it propagates, and then other beams can be affected by that. And this is called a four-wave mixing process. And essentially, you've got this, what we call a virtual level diagram. What the material is doing is taking on the coherent oscillation from two pump photons, and then a third photon, which we call, or a third beam called the signal beam, and it's generating a fourth beam, a new one completely. Okay? This is the mathematics for this process, and it doesn't really matter exactly what this is. The electric field forces the material. It has a linear response described here, and this chi term here, this chi1 term, this typically is of order unity. And then this is the term that generates this mixing process, okay? So you've got this chi3 term, because it's mixing four waves, well, three waves in, one wave out. And this parameter here is small. It's on the order of 10 to the minus 19 meters squared per volt squared. Okay? It's really, really, really small parameter, a weak effect. But the point is that because we can intensify this light in, the combined effect is that this parameter now is getting close to unity. Well, it's not quite. In fact, if it got to unity, everything would break down, this whole analysis. It's about 1/100th of the refractive index. Really, really strong effect. Okay? The nice thing is it's really easy to do. All we need to do is choose a nonlinear material, infiltrate it into the gap, and let's have a look. So this is what we did. Shows nice SEMs. We've got two beams launched onto this grating now, a pump beam and a signal beam, and we generate a third beam that comes out. This is just a nice image to show exactly how nice this gap structure is. And what we've done is measured the efficiency of producing this idler at this point relative to the beams that are injected at this point. Okay? So there's a whole lot of coupling and outcoupling and propagation in and out that we haven't taken into account. We're just looking at the pure effect of creating this idler beam from the light that we get to that point in the first place. Okay? There's a bit of a caveat to these efficiencies. So this is the main result. These are the two beams that are going in at two different wavelengths. This is the pump, stronger beam, and the signal beam. And this is our idler beam. And you may be thinking, well, that doesn't look so efficient. It's about 1% efficient. This is actually quite amazingly efficient because this structure is just 2 microns long. And these nonlinear effects, they take millimeters, centimeters, meters to accumulate in most device technology today. When you account for the fact that we're doing peak-to-peak efficiency, when you account for the whole power transport to this region, it comes out at near a 5% efficiency. We made lots of different structures, and each structure seems to be consistent in producing something that we can explain in terms of the theory. So I just want to state here that the waveguide length you would need to achieve a similar efficiency in other technology. If you were to use an optical fiber, you're going to need 10 centimeters to a meter of fiber to create the same efficiency. If you are going to do this in silicon technology, photonic technology, you'll need a millimeter to a centimeter. And we can do this in a micron. And this is important. It's a very subtle point, but interaction distance actually introduces limitations. If you have to accumulate an effect, because it's very weak, over a meter, the different colors you're trying to mix are all going to travel at different speeds. Over a meter, they're going to go out of phase. And if that happens, the effect gets destroyed. So these devices here can only convert or can only do this process over a very, very restricted range of circumstances. Our technology completely throws all this away. You can do these mixing processes under any conditions, pretty much, over an octave of the spectrum.
And what were the pump and signal wavelengths you were using here?
Oh, sorry. So they were shown here. So these are quite close to telecoms. I think this is down to about 1450, 1480, yeah.
Your wavelength is of the same order as the length of the swap effect.
That's right, exactly. 2 microns. In fact, when we made all these devices, the 2 microns, I think 1 micron was the smallest, but in all the new studies, 2 microns is the longest. We're actually looking at shorter and shorter structures. You can see here that the effect accumulates up to 2 microns, but then if you have longer guides, the effect deteriorates because the energy of the waves is lost because of metallic losses, essentially. Okay, I don't think I've got time to go into the last part. Let me just summarize this and perhaps just give you a taster of the next bit. We've got a very straightforward approach to focusing light on a silicon photonics platform. Really, it's just one geometrical parameter that we have to change. It's really reproducible, and we're quite excited about it. This kind of idea is already being commercialized for modulators, so electro-optic effect for silicon photonics. That's the Swiss group, Leutold at the ETH. We have the potential also to get damage level intensities. I say damage level. We could generate higher intensities potentially. It's just there's no point doing it because we would destroy our material. But at these intensities, there's all sorts of interesting physics that can come out. And it's going to be in portable devices. And another point is that really strong nonlinearity can occur. And when nonlinear processes can be similar in strength to linear processes, I think that's when interesting things will happen in terms of the physics and technology that you can do. So I will give you a 1-minute taster of the last part. And that is something that we've been doing more recently. Metals absorb. So we just saw that you get losses in these really highly confined waveguides. Metasurfaces that are made out of metal are probably only 30-40% efficient. Dielectric ones are much better. So very recently, perhaps in the last 5 years, people are saying, well, can't we use this absorbed light? It turns out that the absorbed energy, it can be useful because it generates things called hot electrons. There's a series of papers in Nature Nanotechnology from 2015 that talk about this topic. These are actually all of them together. They're all on the same issue, back to back. And I recommend that you have a look at them if you're interested in this. What's going on? Well, if you shine light on one of those disks that I'm saying we had in the beginning, what you do is the absorption doesn't just take light away from, doesn't just take energy away from the light field, it gives something. What happens is electrons get excited inside the metal's band structure, and then over a certain amount of time they generate initially a non-thermal population, and then they distribute themselves into something that looks like electrons at a very high temperature. And then gradually, this energy is dissipated amongst the phonon vibrations of the particle, and then you end up with heat being dissipated into your material. So on these different timescales, on very, very fast timescales, what people are doing is chemical reactions. If your electrons are at 1,000 or 2,000 Kelvin, it means they've got energy to activate reactions that couldn't occur before. People are doing water splitting, Sabatier reaction of making methane from carbon dioxide. These are all really interesting things that people are doing, and you can do this from sunlight too. Cancer treatment. So this is treating a mouse which was unfortunately infected with cancer cells. What happens here is that over a long period of time it takes to dissipate the heat from these particles, what they do is they functionalize these particles that seek out cancer cells, and then they fire a laser beam at it, and you only heat up the particles that are attached to the cancer cell and destroys it. We're doing things with photoacoustics, and people are also making photodetectors. And the nice thing here is that if your electrons are really, really hot, you can make a photodetector that is not linked to the band gap of the material you're using. So this would be the last part of my talk, which I'm not going to go into. If you can use metal structures to create photodetection, so convert optical energy into electrical energy without needing a material with a band gap. And I'm happy to talk about that later, but I shall stop now in the interest of discussion. Thank you for your attention.
Wonderful, thank you so much. I shall never look at metal samples the same way again. Any questions?
For the last part that you have metal waveguides, did this nonlinear experiments in quiet temperatures for quantum applications?
High temperatures for?
Yeah, it's cryo temperatures.
No, these were conducted at room temperature. So the limitations are damage. If you use too much laser intensity, it will destroy the material that's inside the gap. unfortunately, we selected a number of materials which we thought suitable, but the one we ended up with, which had the best characteristics, also happened to degrade in ambient environment, but there are plenty of materials that don't. Essentially, there are not many real limitations to using this in the future. The one thing that is a problem is that the use of organic materials like this in a fabrication environment, like a fab lab or a foundry, is not tested. And that's perhaps the only block, I think, to getting this working. For instance, anything to do with silicon, they hate gold. And actually, our structures are made out of gold. You're going to have to change that to make it work as well. Gold forms traps in silicon that ruins electrical properties. But those are the only limitations, just in terms of technological limitations of the materials. But there are other materials that we can use.
Excellent talk. In your work of forward mixing, you have shown that the conversion efficiency decreases with the length of your structure, and this is due to loss.
Yeah.
Is this fundamental? Can we avoid? Because obviously you said your size is much smaller compared to the size of fibers or silicon or whatever, but obviously there the losses is so low that you can have kilometers if you wish to. So
Yeah, so you're right. When it comes to nonlinear effects, interaction distance will always win. You can make a fiber a kilometer and it will be, you can make it to be 100% efficient. Well, I don't know quite 100%, but in doing that, you have to really play carefully with the parameters, because these waves, as they propagate, they're all interacting with each other and energy being transferred from one to the other over long distances. So I'd say yes, you can get the efficiency if you make it longer with any technology apart from plasmonics, which you can't make longer. The great thing here is the flexibility that's afforded by being a broadband phenomenon. It's not restricted to how fast the colours move with respect to each other. I didn't talk about it, but the colours go out of phase in this particular experiment over 200 microns, whereas we're working over 2. We're also looking at smaller structures and not larger. We think that if we go to smaller structures with smaller gaps, actually the efficiencies are going to be better. The point of this plot here says that there is actually no point in working with a waveguide longer than 2 microns.
That's right. Yeah.
Right? And that all your effect is coming from here. And the modelling that we're using is probably not good enough for actually describing what's going on. When we work in this regime here, it's pretty much unknown what's going to happen. For instance, you can see here that this point should be probably quite a lot lower than it really is. This is a logarithmic scale. So something weird is going on here, and so that's what we're doing now. We're working on really, really small structures to see just how much we can squeeze out of it.
But the losses are fundamental. You can't do anything.
The losses are fundamental, but remember that at this point, there's really just 50 dB loss. This is equivalent to, well, perhaps a little bit more than that. This is about the propagation length, so just a bit more than 3 dB loss, which for these kind of structures I think is at least tolerable for proof of principle. Yeah. I agree. I think that there's a lot to be done before we can really exploit this.
I was just curious if it was fundamental or...
We're also interested by being unrestricted by this problem of the colours propagating at the same speed. We reckon that in this case, these wavelengths are chosen simply because the coupling optics have a limited bandwidth. In fact, we can't go to 1400 because this envelope is where light actually, you can shine a beam and get it into the structure and out of it as well. But with careful thought about how to do that in a much more broadband nature, there's no reason why we can't start getting 1500 nanometers to talk to 2 microns to talk to 3 microns. Now, when you're doing that, eventually all other approaches dry up. You just can't use anything else. So even though our efficiencies may not quite be there, there are certainly things that we can do that other techniques can't. And I think that's another reason, another way to push this. very good question.
For the biomedical applications of the hot electrons that you showed right at the end, and I'm not sure how familiar you are with it, do you know how much the functionalization changes the properties of the particles they work with?
Yeah, so if you put a shell of just really any sort of dielectric material in a shell around a particle, it will modify its resonance, but quite a small amount, actually. There are people who play with... a bigger problem may be agglomeration of particles. So there are people who play around with molecular rulers where they measure essentially the average distance between particles, which can affect the resonances. But these are really, really small effects. In terms of just delivering heat to an object, I don't think there's any problem. And this functionalization is designed... What they'll do is they'll look at the cancer cell, they'll look at the antibodies involved, and then they will literally program that particle to respond to that type of cell. So it's really, really specific as well. And then the laser beam is applied fairly locally. It's not going to damage tissue because the intensity is designed to heat the particles, not the material. It's the particles, then they heat the material. Yeah, I'm sorry I didn't have time to go into that. I really, really wanted to, but yeah.
Any more questions? This ability to generate such high intensity light, and as I understand it, also to control it, to localize it very precisely. How would you see that being used to further our knowledge of the interaction between light and matter?
So by knowledge, I'm thinking physics and mathematics. If you think about it in that term, this equation here tells you how a material polarizes. You usually think about electrons sitting in, we always think about oscillators. So that would be some electron that's bound in a position, and when we shine light on it, it will move around that position. And I know when I was doing A-levels or something, you just assume that everything is a harmonic potential, like a quadratic potential. And so the restoring force is linear. But it turns out that, well, I think you can pretty much understand that electrons, when they're in atoms, this potential is not quadratic, and that they can move and have these higher order terms. And usually what you do, because the electrons are not driven too much, they're just a little bit beyond harmonic, you generate these perturbative expansion, it's called. So there's a chi2 term, a chi3, chi4, chi5, and these higher order terms describe the potential landscape in which the electron moves. This actually breaks down, this perturbation expansion only works when the electron's still pretty much confined to the potential. So these higher order terms they should die away quickly if this analysis is valid. So there's a whole area of physics now, which I think is called attosecond physics. And this revolves around the idea that you're driving electrons so far from their equilibrium positions that this perturbative expansion breaks down. And while you would expect each of the successive terms to get successively smaller, what starts to happen is these higher order terms actually sustain themselves, and you get these plateaus where, for instance, people are generating the 111th harmonic of an infrared beam. This means you can get into the UV range with lasers. And not only that, these processes, because they're really broad band and lots of pulses that are essentially in phase, these are also attosecond pulses. So attosecond physics is all about vacuum chambers and gases and really controlled environments which require lab conditions. But very recently, perhaps the last 5 years, people have been talking about solid state high harmonic generation. So now we're talking about, I think it's very open to think what we can do with this kind of physics, but we're talking about vast ranges of wavelength generation, so different light sources with different colors, very, very fast processes, potentially doing new types of spectroscopy with solid-state devices, portable devices, so you can bring attosecond physics out of the lab and into portable devices. So that's one of the things that I'm very interested in. So in terms of the science, you break down this perturbative description, and there may be some really nice applications to come from that too.
I'm sure you've got people thinking about that in the context of some of the work we're doing here, so thank you so much.
Cool.
Any last questions? Otherwise we can go and have a chat upstairs. Okay, let's thank them once more and
Thank you.